Greetings, everybody. I wanted to give you all some more Lewis structures practice. So here we have three different molecules: the nitrate ion, an acid, which in this case I've chosen chlorous acid, and the last molecule is another acid, hydrocyanic acid. And we're going to draw their Lewis dot structures, okay? So without further ado, we're going to start with the nitrate ion. As well, I want to say any point of this video, feel free to hit pause on your keyboard by hitting the space bar or selecting pause on the screen, and see if you can figure out or work ahead of me and see if you can figure some of these out as we're working along. I strongly encourage you to do that. All right, let's do nitrate. So remember the first step in every Lewis structure. You must do this. We need to calculate the total number of valence electrons. So here we go. The nitrogen has 5 valence electrons, and we're going to add to that 3 times 6 valence electrons. Now here's a very important point, so please pay attention. Notice that nitrate has a minus charge. Because nitrate has a minus charge, or 1 additional electron, that means that we have to come in here and add 1 additional electron. And so if we add all of those together, we get, so students, remember this is the golden rule, the one rule we cannot break, right? Our structure that we draw, whatever we come up with, has to have 24 valence electrons. So just looking at the formula and how it's written, it would appear that nitrogen is our central atom. And so what I'm going to do is place it at our center, and then I'm just going to put oxygens around it. So what we're doing again is our skeletal structure. Again, a skeletal structure means no electrons of any kind have been added. We're just placing our atoms roughly in where we think they might go. The next step to this would be to draw single bonds. So 1, 2, 3. The next step is to, using lone pairs, start adding lone pairs until we've reached an octet for every single atom in our diagram. Notice that this nitrogen has 3 shared pairs, which means I need 1 lone pair. And then each oxygen is the same. Each oxygen only has 1 shared pair, or 2 electrons, which means each oxygen needs 6 more electrons for a total of 3 lone pairs apiece. And so this is our first proposal, if you will, for the structure of the nitrate ion. Now we have to make sure that the total number of electrons in our structure will actually equal 24. So here we go. Remember, there's different ways of counting. I think the easiest way to do it is to count by the octet rule, which means then that this is 8, 16, 24, 26. So this structure has 26 electrons. Notice that this is not 24 electrons, which means then that this cannot be the correct structure. So what do? How do we fix this structure? Well, the one thing that we can try is to make a double bond. I'm going to choose this bond between the nitrogen and oxygen, and I'm going to make that a double bond. But notice if I make this a double bond, I need to go back and correct for octet rule, which means I don't need that lone pair on the nitrogen, and I don't need a lone pair on the oxygen. So looking at this structure, let's go through and see if we now have 24 valence electrons. So here we go. Notice now we have 8, 16, 24. And looky there. So this may very well be our structure. This is the nitrate ion. Let's enhance our structure by adding some formal charges. So the formal charge for this oxygen is 6 valence electrons. Subtract off the number of shared pairs minus the total number of dots with the total number of electrons in the lone pairs, which would be 4. So that has a formal charge of 0. Notice that these two oxygens are identical, and so their formal charges would be the same. That would be 6 valence electrons minus 1 shared pair minus the total number of dots, which would be 2, 4, 6. And looky here, we have minus 1. So how do we write that in our structure? Well, in our structure, we're going to include a minus sign here and here in the upper right corner of those atoms, no matter how they're positioned. And so those are now finished. Let's now do the nitrogen. So to do the nitrogen, it has 5 valence electrons. It has 1, 2, 3, 4 shared pairs and no lone electrons, which that equals plus 1. And so on the nitrogen, anywhere we can, we're going to write a plus. Now what we want to do is check for resonance structures. If you haven't watched my video on resonance structures, go watch it real quick. I promise you it'll explain everything. Looking at nitrogen though, there it has an obvious 2 additional resonance structures. Let's draw them now. So there is 1 additional resonance structure. Now let's do our final resonance structure. And so here is our third and final resonance structure for the nitrate ion. Because nitrate is an ion, we do need to enclose it in brackets, and we do need to write its charge. And because the resonance structures, but traditionally we would write a little double-headed arrow in between. And so this would be the formal way of writing the resonance structures for the nitrate ion. Now let's take a look at chlorous acid. Chlorous acid has a total of 1 electron from the hydrogen, 7 electrons from the chlorine, and 2 times 6 electrons for each oxygen. Adding all of that together, you're going to get 20 valence electrons. All right, so just to remind everybody, that's the total number of electrons we have to work with. Okay, so without further ado, looking at this structure, now let's talk about acids for a minute. How do I orchestrate it? Well, in doing the skeletal structure, it seems like the best choice would be chlorine. And if that's the way that you went, you are right. Chlorine is the least electronegative atom, and the least electronegative atom is usually our atom that we would write as our central atom. Hydrogen can never be a central atom. So you might feel initially like this would be our skeletal structure. And that might make you think, okay, that's it, that's got to be it. So as it turns out, students, this is not the proper skeletal structure. And the way that we can tell is because we have an oxoacid. Remember, an oxoacid is an acid that has oxygens in it. So remember this, when you have an oxoacid, you want to attach the hydrogen onto one of the oxygens in the structure. So what I'm going to do to properly do this structure is I'm going to move some of these elements around a little bit. I'm going to move my hydrogen off of that oxygen, and I'm going to move this oxygen over here just for looks reasons. So this is a better way of drawing the the skeletal structure for chlorous acid. Let's move on to our next step. We're going to add single bonds to between every single atom. Complete octets. Everyone has now their completely filled valence shell, or 8 valence electrons. Now let's count these up. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So this is our Lewis structure for HClO2. And again, I want to stress, that we did achieve 20 electrons in our structure. Let's assign formal charges. So looking at our formal charges, for this oxygen, we have 6 valence electrons minus 1 shared pair minus the total number of electron dots, which is, or electrons in lone pairs, which would be 6. So that comes out to be a total of -1. So now we know that this oxygen here will carry a slight negative charge. If we were to do the chlorine now, its formal charge would be 7 valence electrons minus 2 shared pairs minus a total of 4 dots, or 4 electrons in your lone pairs. And 7 minus 2 minus 4, I bet you'll see that's going to be a +1. So let's go write that in. So chlorine has a plus charge. Doing this again, this oxygen has a formal charge of 6 valence electrons minus 2 shared pairs minus 4 electrons in your lone pairs. So that would be 0. And then of course hydrogen is 0. Now that we have done formal charges, we need to ensure that our formal charges mesh or agree with what we understand about electronegativity. So what do I mean by that? What we want to do is make sure that in all cases, in every bond, that the most electronegative atom was assigned the most negative formal charge. So, in the case of this chlorine, notice that both oxygens are technically more negative than the chlorine. This oxygen has a formal charge of -1, and this oxygen right here has a formal charge of 0, both of which are more negative than the positive chlorine. If you go look at your electronegativity chart, you can see that oxygen is more electronegative than chlorine. Now that tells me that this structure has been validated by means of formal charge. Looking at this structure, there are no resonance structures, and this is not an ion, which means then that this is our final answer for the Lewis structure of chlorous acid. Let's do our final example, hydrocyanic acid. As always, we start with count the total number of valence electrons. So for this molecule, that would be 1 electron from the hydrogen, 4 electrons, valence electrons for carbon, and then of course 5 valence electrons for nitrogen. And if you add all those together, you're going to get a grand total of 10 electrons. Now because we have a carbon atom in our structure, then I know that's going to be my central atom. Equally stated, the least electronegative atom will be your central atom. And of course it can't be hydrogen, so that leaves carbon. So let's write our carbon first. And it looks like the structure I'm imagining right now, maybe you are too, is going to look very similar to the actual formula. So I'm just going to write it like this. So the next step is to write our skeletal structure. Now that we're complete with our skeletal structure, we're going to add single bonds between all atoms. Now we're going to go and add all lone pairs necessary until we have reached or achieved a valence or an octet rule for all atoms. Of course, hydrogen is always just 1 bond. So this carbon needs 2 lone pairs or another 4 electrons, and this nitrogen needs an additional 6 electrons, so 3 lone pairs. Now let's count the total number of electrons that we have available, or that we placed in our structure. So we have 2, 4, 6, 8, 10, 12, and then 14. So right now we've got a big problem. Okay. So right now we've got a big problem, and that problem is we have 14 electrons. Big problem. How do we fix this problem? Well, the best way that we can fix this problem by looking at our structure is we probably want to try to add a double bond. So, looking at the structure, there's only one location where that can be done because hydrogen cannot have more than 2 electrons. So therefore, carbon to nitrogen is where we can add it. Let's add it. If you add a double bond, and this is true for a triple bond, then you need to erase a lone pair on both atoms in that bond. So I'm going to erase that lone pair and that lone pair. Why do we do that? It's to ensure that we have maintained 8 electrons per atom. So let's go through and count again. So let's go through and count again now that we have changed our structure. Here we go. 2, 4, 6, 8, 10, now 12 electrons. So this structure has 12 electrons. That's still a no, right? Because we can only have as many, or at most 10, and as least 10, right? We have to have 10 electrons. What's the only thing that we can do now? Let's now try to add a triple bond. So to add a triple bond, we will now go in and have to erase a lone pair if we go from a double to a triple, to ensure that each atom in our structure is still agreeing with the octet rule. Notice that now carbon has 8 valence electrons in its structure, as does nitrogen. Hydrogen still has 2. Let's go count these now. That's 2, 4, 6, 8, and then 10. So this has 10 electrons. Let's now do formal charges. So our formal charge for hydrogen should always be 0, and carbon should always be 0. And you can check out that carbon, as long as you have not placed any lone pairs on carbon and just 4 shared pairs on carbon, it'll have a formal charge of 0. We will check the nitrogen though. Nitrogen is 5 valence electrons minus 3 shared pairs minus 2 electrons in our lone pairs, or 2 dots. That of course equals 0. So every single atom in our structure has a formal charge of 0. I did forget to mention that chlorous acid has a charge of 0. So let's check our formal charges by adding them together. And if you do that carefully, you will notice that the sum of our formal charges is 0, which is equal to the charge of chlorous acid, 0. Remember, the sum of your formal charges should always equal the charge of your molecule.